Nanomaterials can be work as the functional nanosurfaces. Nanosurfaces indicate either the surface-modified nanomaterials or functionally modified surface of the nanomaterials. Let us first think about the surface-to-volume ratio as a function of size of the nanomaterials. As shown in this table, the surface-to-volume ratio inversely decreases with increasing the size. The motivation of preparation of nanosurfaces is its wide applications. For example, we can use surface-functionalized nanoparticles for the molecular recognition of protein, DNA, saccharide. Molecular recognition is a critical tool to design antibody, genetics, drug discovery, and so on. For example, enzyme-linked immunosorbent assay abbreviated as ELISA, microarray, immunoassay, biotin streptavidin, protein labeling, amine reactive labeling, sulfhydryl labeling, and gene chip are the product of the nanosurfaces. This can be further applied to detect or report dye, quantum dots, surface plasmonic resonance, surface-enhanced Raman scattering. The modified surface of the nanomaterials can be applied for separation such as gel, chromatography and magnetic field-driven filtering. As helpful information for students, I would like to talk about nanosurfaces a little bit. Before we learn the nanosurface, let me introduce basics for you. First of all, it is important to learn about the surface and interface energy. Creating surfaces costs energy. This is due mainly to the additional free energy generated by the atoms at the surface which make contact with heterogeneous materials. The surface and interface energy depends on the chemical affinity of the surface and the surrounding materials. For example, water-air interface requires 72 mN per meter to make the interface, while water-oil requires 50, and mercury-air requires 490 mN per meter. When liquid droplet is placed on the surface, there exists three components. First one is the liquid, second one is the solid substrate, and the third one is the surrounding media. Therefore, we can use the three interface energies to calculate the equilibrium contact angle of the liquid droplet using this relationship in the left figure. When the liquid is water, the contact angle acts like a standard to determine the surface properties. For example, the surface is called hydrophobic, which means that the surface dislikes the water, if the contact angle is greater than 90 degrees. In contrast, if the contact angle is smaller than 90 degrees, the surface is called hydrophilic, which means that the surface likes the water. The contact angle of the liquid droplet can also be manipulated by the surface textures such as nanostructures surfaces. In Wenzel's model shown in the left column, the liquid drop is assumed to fully contact the nanotextures. This can be represented by introducing the surface roughness factor, R. R is the ratio between the surface area solid liquid and the flat projected area. Using the engineered nanosurfaces, we can prepare perfectly wetting surface with the intrinsically hydrophilic surfaces. In contrast, when start with intrinsically hydrophobic surface, the hydrophobicity is even increased to make the contact angle nearly equal to 180 degrees. This surface is called superhydrophobic surfaces. In nature, a lotus leaf is close to the superhydrophobic surface. This make the lotus leaf as self-cleaning surfaces. There is another model for the nanotexture. This model is called as Cassie-Baxter or Cassie's model. In this model, the liquid droplet is assumed to contact the part of the nanotextures, particularly the protruded parts. The effective contact angle can be calculated by considering the fraction of the protruded part as shown in the right column. Both model can partially the effective contact angle, and therefore, when combined, the two model can explain the variation of the contact angle induced by the nanotextured surfaces. One of the important materials for the surface modification is surfactant. Surfactants are molecules that lower the interfacial energy. They are composed of two parts. The first part is head, which is mainly polar, ionic, hydrophilic, and sphere-like. The other part is tail, which is apolar, non-ionic, thread-like, and hydrophobic. Surfactants can match two chemically heterogeneous materials into one interface. This is done by the decrease in the interface when intervened by the surfactants. For examples, the surfactants at the oil-water can decrease the interface energy. Due to the head-tail heterogeneity, the surfactants can spontaneously form self-assembled structures such as lipid bilayers, micelle spheres, cones, and so on. It is possible to modify either head or tail to tailor the assembly properties. In addition, the tail and the head can be chosen to modify the surface of nanoparticles. For example, oleic acids and amines can be used as the surfactants for metallic nanoparticles to control the assembly of the nanoparticles. Based on the surface area to volume effect, nanoscale materials have 1. Increased total surface area. 2. Increased number of atoms accessible on the surface. 3. Increased catalytic activity of those large number surface atoms. 4. Different, tunable surface catalytic properties by the change in shape, size and composition. Hence, nanoscale catalysts can increase the rate, selectivity and efficiency of various chemical reactions. In particular for the catalytic effects of the nanomaterials, it is important to control the structural disorder of the materials. For example, structural defects in the nanocrystals such as steps, kinks, dangling bones can work for the catalytic sites to facilitate the chemical reactions. Nanomaterials have the structural features in between of those of atoms and the bulk materials. While most microstructured materials have similar properties to the corresponding bulk materials, the properties of materials with nanometer dimensions are significantly different from those of atoms and bulk materials. This is mainly due to the nanometer size of the materials which render them. The nanometer size effects give large fraction of surface atoms, high surface energy, spatial confinement, reduced imperfections, which do not exist in the corresponding bulk materials. Due to their small dimensions, nanomaterials have extremely large surface area to volume ratio, which makes a large to be the surface or interfacial atoms, resulting in more surface-dependent material properties. Especially when the sizes of nanomaterials are comparable to length, the entire material will be affected by the surface properties of nanomaterials. This in turn may enhance or modify the properties of the bulk materials. For example, metallic nanoparticles can be used as very active catalysts. Chemical sensors from nanoparticles and nanowires enhance the sensitivity and sensor selectivity. The nanometer feature sizes of nanomaterials also have spatial confinement effect on the materials, which bring the quantum effects. In particular, because of the quantum confinement in nanomaterials, the emission of visible light can be tuned by varying the nanoscale dimensions. It is observed that the size reduction in nanomaterials shifts the emission of peak towards the shorter wavelength, which is called as blue shift. The energy band structure and charge carrier density in the materials can be modified quite differently from their bulk and in turn will modify the electronic and optical properties of the materials. For example, lasers and light-emitting diodes from both of the quantum dots and quantum wires are very promising in the future optoelectronics. High-density information storage using quantum dot devices is also a fast-developing area. Reduced imperfections are also an important factor in determination of the properties of the nanomaterials. Nanostructures and nanomaterials favors of a self-purification process in that the impurities and intrinsic material defects will move to near the surface upon thermal annealing. This increased materials perfection affects the properties of nanomaterials. For example, the chemical stability for certain nanomaterials may be enhanced, the mechanical properties of nanomaterials will be better than the bulk materials. The superior mechanical properties of carbon nanotubes are well known. Due to their nanometer size, nanomaterials are already known to have many novel properties. Many novel applications of the nanomaterials rose from these novel properties have also been proposed. Firstly, let's us look at the optical properties of nanomaterials. One of the most fascinating and useful aspects of nanomaterials is their optical properties. Applications based on optical properties of nanomaterials include optical detector, laser, sensor, imaging, phosphor, display, solar cell, photocatalysis, photoelectrochemistry and biomedicine. The optical properties of nanomaterials depend on parameters such as feature size, shape, surface characteristics, and other variables including doping and interaction with the surrounding environment or other nanostructures. Likewise, shape can have dramatic influence on optical properties of metal nanostructures. With the CDC semiconductor nanoparticles, a simple change in size alters the optical properties of the nanoparticles. When metal nanoparticles are enlarged, their optical properties change only slightly as observed for the different samples of gold nanospheres. However, when an anisotropy is added to the nanoparticle, such as growth of nanorods, the optical properties of the nanoparticles change dramatically. Electrical properties of nanoparticles discuss about fundamentals of electrical conductivity in nanotubes and nanorods, carbon nanotubes, photoconductivity of nanorods, electrical conductivity of nanocomposites. One interesting method which can be used to demonstrate the steps in conductance is the mechanical thinning of a nanowire and measurement of the electrical current at a constant applied voltage. The important point here is that, with decreasing diameter of the wire, the number of electron wave modes contributing to the electrical conductivity is becoming increasingly smaller by well-defined quantized steps. Otherwise, we can measure electrical conductivity of a nanowire with application of mechanical strain, which will modify the electronic structure of the semiconductor crystalline structure of the nanowire. This property can be applied to fabricate a nanomechanical sensor to measure the strain as shown in the left figure. In electrically conducting carbon nanotubes, only one electron wave mode is observed which transport the electrical current. If the nanotube structure is armchair, then the electrical properties are metallic. Theoretically, metallic nanotubes can carry an electrical current density much faster than typical metal, such that 1000-fold conductivity. However, the structure is chiral and then, the electrical properties can be either semiconducting with a very small band gap, otherwise the nanotube is a moderate semiconductor. In bulk materials, conduction of electrons is delocalized, that is, electrons can move freely in all directions. When the scale is reduced to nanoscale, the quantum effect dominates. For zero-dimensional nanomaterials, all the dimensions are at the nanoscale and hence the electrons are confined in 3D space. Therefore no electron delocalization, freedom to move, occurs. For one-dimensional nanomaterials, electrons confinement occurs in 2D space and hence electron delocalization takes place along the axis of nanotubes/nanorods/nanoirs. Due to electron confinement, the energy bands are replaced by discrete energy states which make the conducting materials to behave like either semiconductors or insulators. In principle, we can expect the enhancement of mechanical properties of materials at nanoscale. This is mainly because of the fact that the nanoscale materials can reduce the grain size, increase the structural disorder and surface of grain boundary, make more barriers for dislocation movement. These factors make mechanically stronger materials at nanoscale. Mechanical properties of nanoparticles deals with bulk metallic and ceramic materials, influence of porosity, influence of grain size, superplasticity, filled polymer composites, particle-filled polymers, polymer-based nanocomposites filled with platelets, carbon nanotube-based composites. The discussion of mechanical properties of nanomaterials is, to some extent, only of quite basic interest, the reason being that it is problematic to produce macroscopic bodies with a high density and a grain size in the range of less than 100 nanometers. Experimental studies on the mechanical properties of bulk nanomaterials are generally impaired by major experimental problems in producing specimens with exactly defined grain sizes and porosities. Therefore, model calculations and molecular dynamics studies are of major importance for an understanding of the mechanical properties of these materials. Good mechanical properties of nanomaterials can be applied to produce tough and flexible materials. For example, filling polymers with nanoparticles or nanorods and nanotubes, respectively, leads to significant improvements in their mechanical properties. Such improvements depend heavily on the type of the filler and the way in which the filling is conducted. The latter point is of special importance, as any specific advantages of a nanoparticulate filler may be lost if the filler forms aggregates, thereby mimicking the large particles. Particulate-filled polymer-based nanocomposites exhibit a broad range of failure strengths and strains. This depends on the shape of the filler, particles or platelets, and on the degree of agglomeration. In this class of material, polymers filled with silicate platelets exhibit the best mechanical properties and are of the greatest economic relevance. The larger the particles of the filler or agglomerates, the poorer are the properties obtained. Although, potentially, the best composites are those filled with nanofibers or nanotubes, experience teaches that sometimes such composites have the least ductility. On the other hand, by using carbon nanotubes it is possible to produce composite fibers with extremely high strength and strain at rupture. Among the most exciting nanocomposites are the polymer ceramic nanocomposites, where the ceramic phase is platelet-shaped. This type of composite is preferred in nature, and is found in the structure of bones, where it consists of crystallized mineral platelets of a few nanometers thickness that are bound together with collagen as the matrix. Composites consisting of a polymer matrix and defoliated phyllosilicates exhibit excellent mechanical and thermal properties. The size of magnetic nanoparticles also influences the value magnetization. For example, the saturation magnetization of zinc ferrite increases with decreasing the size of the nanoparticles. The magnetization increases significantly below a grain size of 20 nanometers. Hence, By decreasing the particle size of a granular magnetic material, it is possible to improve the quality of magnets fabricated from it. Bulk gold and PT are non-magnetic, but at the nano size they are magnetic. The magnetic properties can be classified into three categories such that ferromagnetism, paramagnetism, and superparamagnetism. These classification can be differentiated using magnetic hysteresis as shown in the upper right plots. Magnetic hysteresis occurs when an external magnetic field is applied to a ferromagnet such as iron and the atomic dipoles align themselves with it. Surface atoms are not only different to bulk atoms, but they can also be modified by interaction with other chemical species, that is, by capping the nanoparticles. This phenomenon opens the possibility to modify the physical properties of the nanoparticles by capping them with appropriate molecules. Actually, it should be possible that non-ferromagnetic bulk materials exhibit ferromagnetic-like behavior when prepared in nano range. One can obtain magnetic nanoparticles of palladium, of platinum, and the surprising case of gold, which is diamagnetic in bulk from non-magnetic bulk materials. In the case of platinum and palladium, the ferromagnetism arises from the structural changes associated with size effects. However, gold nanoparticles become ferromagnetic when they are capped with appropriate molecules. The charge localized at the particle's surface gives rise to ferromagnetic-like behavior. Surface and the core of O nanoparticles with 2 nanometers in diameter show ferromagnetic and paramagnetic character, respectively. The large spin-orbit coupling of these noble metals can yield to a large anisotropy and therefore exhibit high ordering temperatures. More surprisingly, permanent magnetism was observed up to room temperature for thiol-capped gold nanoparticles. For nanoparticles with sizes below 2 nanometers, the localized carriers are in the 5D band. Bulk gold has an extremely low density of states and becomes diamagnetic, as is also the case for bare gold nanoparticles. This observation suggested that modification of the D-band structure by chemical bonding can induce ferromagnetic-like character in metallic clusters. Magnetic nanoparticles have been actively employed for various areas such as medical imaging, including MRI, PET, and fluorescence. On the right figure, you can find diverse applications of magnetic nanoparticles for MRI. They can work for a carrier of DNA, chemicals, drugs, and proteins for therapeutic purposes. It can also be used in molecular recognition systems such as polymer shrinking, DNA dehybridization, and protein cleavage. With external field, the magnetic nanoparticles can be used for cell stimulation. Iron oxide nanoparticles are the most popular and most easily preparable magnetic nanomaterials. Using hydrothermal synthetic route, it is possible to synthesize 5 to 50 nanometers size iron oxide nanoparticles in aqueous solution or organic solvents. However, there is a problem in preparation of the magnetic nanoparticles. This is the short-range attractive interaction among the magnetic nanoparticles. They work as small magnets to each other, which lead them to form assembled structures such as clusters, chains, rings, and so on. For the applications, the clustering is not desirable since it is important to maintain the small size of the magnetic nanoparticles. To prevent the assembly and clustering, the magnetic nanoparticles can be surface modified using organic molecules such as oleic acids or oleic amines. In addition, it is possible to treat the surface of the nanoparticles using DNA or small molecular rigid functional moieties. Recently, surface ligands can be expanded to the biological receptors for the biomedical applications as well as controlling the clustering as shown in the left figure. When the magnetic nanoparticles are dispersed in liquid solution with stability, they form colloidal solution. This colloidal solution is called ferrofluid. By applying external magnetic field, it is possible to control the movement and even periodic arrangement of the colloidal solution. The peculiar patterns for shapes of the ferrofluid is due mainly to the hydrodynamic instability given by the concentration gradient of nanoparticles in the solution driven by the magnetic field. Ferrofluid has been actively used for various areas such as sealant for rotary shaft in a vacuum devices as shown in the upper right figure and coolant for overheated speakers as shown in the lower right figure. We have explored various properties of nanomaterials. By understanding of the physical and chemical, and even biological properties of the nanomaterials, we can expand the application potentials of the nanomaterials into a lot of areas. As provided in the left illustration's large surface-to-volume ratio, strong oxidizing performances, mechanical hardness, electrical conductivity, and paramagnetism as a function of size can be applied to fabricate hydrogen catalyst, antibacterial properties, flexible and mechanically tough composite materials, efficient solar cells, field effect transistors, and magnetically controllable agents. Let us explore some specific applications of the nanomaterials. First case is a fuel cell, which is an electrochemical energy conversion device that converts the chemical energy from fuel and oxidant directly into electricity. The heart of fuel cell is the electrodes. The performance of a fuel cell electrode can be optimized in two ways, by improving the physical structure and by using more active electrocatalyst. A good structure of electrode must provide ample surface area, provide maximum contact of catalyst, reactant gas and electrolyte, facilitate gas transport and provide good electronic conductance. In this fashion the structure should be able to minimize losses. Carbon nanotubes have chemical stability, good mechanical properties and high surface area, making them ideal for the design of sensors and provide very high surface area due to its structural network. Since carbon nanotubes are also suitable supports for cell growth, electrodes of microbial fuel cells can be built by using the nanotubes. Due to three-dimensional architectures and enlarged electrode surface area for the entry of growth medium, bacteria can grow and proliferate and get immobilized. Multi-walled nanotube scaffolds could offer self-supported structure with large surface area through which hydrogen-producing bacteria such as E. coli can eventually grow and proliferate. Also nanotubes have been reported to be biocompatible for different eukaryotic cells. The efficient proliferation of hydrogen-producing bacteria throughout an electron-conducting scaffold of nanotubes can form the basis for the potential application as electrodes in fuel cells leading to efficient performance. The second case is catalysis. Higher surface area available with the nanomaterial counterparts, nanocatalysts tend to have exceptional surface activity. For example, reaction rate at nanoaluminum can go so high that it is utilized as a solid fuel in rocket propulsion, whereas the bulk aluminum is widely used in utensils. Nanoaluminum becomes highly reactive and supplies the required thrust to send off payloads in space. Similarly, catalysts assisting or retarding the reaction rates are dependent on the surface activity, and can very well be utilized in manipulating the rate controlling step. The third case is display materials. The resolution of a television, or a monitor, depends greatly on the size of the pixel. These pixels are essentially made of materials called phosphors, which glow when struck by a stream of electrons inside the cathode ray tube. The resolution improves with a reduction in the size of the pixel, or the phosphors. Nanocrystalline zinc selenide, zinc sulfide, cadmium sulfide, and lead telluride synthesized by the sol gel techniques are candidates for improving the resolution of monitors. The use of nanophosphors is envisioned to reduce the cost of these displays so as to render HD TVs and personal computers affordable to be purchased. The fourth case is next-generation electronics circuit. The microelectronics industry has been emphasizing miniaturization, whereby the circuits, such as transistors, resistors, and capacitors, are reduced in size. By achieving a significant reduction in their size, the microprocessors, which contain these components, can run much faster, thereby enabling computations at far greater speeds. However, there are several technological impediments to these advancements, including lack of the ultrafine precursors to manufacture these components, poor dissipation of tremendous amount of heat generated by these microprocessors due to faster speeds, short mean time to failures, poor reliability, etc. Nanomaterials help the industry break these barriers down by providing the manufacturers with nanocrystalline starting materials, ultra-high purity materials, materials with better thermal conductivity, and longer-lasting, durable interconnections, connections between various components in the microprocessors. The fifth is for the environmental purpose. Nanomaterials possess extremely large grain boundaries relative to their grain size. Hence, they are very active in terms of their chemical, physical, and mechanical properties. Due to their enhanced chemical activity, nanomaterials can be used as catalysts to react with such noxious and toxic gases as carbon monoxide and nitrogen oxide in automobile catalytic converters and power generation equipment to prevent environmental pollution arising from burning gasoline and coal. The sixth is the advanced sensor. Sensors rely on the highly active surface to initiate a response with minute change in the concentration of the species to be detected. Engineered monolayers on the sensor surface are exposed to the environment, and the peculiar functionality such as change in potential is utilized in sensing. Finally, it is also relevant to mention of the nanomaterials in cosmetics. Prolonged UV exposure causes skin burns and cancer. Sunscreen lotions containing nanotitania provide enhanced sun protection factor while eliminating stickiness. The added advantage of nanoskin blocks such as zinc oxide and titania arises as they protect the skin by sitting onto it rather than penetrating into the skin. Thus they block UV radiation effectively for prolonged duration. Additionally, they are transparent, thus retain natural skin color while working better than conventional skin lotions. Actually, due to the peculiar properties of the nanoparticles, we can expand the applicability of the materials into a variety of areas including food, agriculture, energy, biotechnology, healthcare, mobility, textiles, construction, energy technology, environment, electronics, and computer science. Therefore, if you want to apply your nanomaterials, there are numerous ways waiting for you to be touched by your materials. However, this also means that it requires some distinguishable properties of your materials from other conventional nanomaterials. Therefore, please remember that the nanomaterials should be equipped with notably distinct physico-chemical properties or mass production potential or ease of modification for the better applications.